Hello everybody. In this video we're going to talk about eigenvalues and saddle points, which is from section 14.7. First we give a definition of local maximum and local minimums. Given a function f of xy, two variables, a function of two variables, then it gives a surface in 3D space. And by local maximum, we mean the point AB, its function value is greater than or equal to all other values in an open disk centered around AB. So, which means, this intuitively speaking, local maxima correspond to mountain peaks on the surface z equals f of x, right? So, which means this point is local maximum because you can draw a neighborhood of this point, and within this region, the point is the greatest value. And also there's another local maximum like this. And this also tells us there might be multiple local maximums depending on the surface. And among all local maximums, we define global maximum as the greatest local maximum, which in this picture, this is global maximum. And local minimum is opposite. Local minimum correspond to valley bottoms, which is defined as f of AB is less than or equal to other values in an open disk centered around AB. So this is obvious local minimum. All right, our question is, given a function, how to find local maximum and minimums. So first, we introduce first order condition, FOC. It says, given a function of xy, if AB is interior point which corresponds to either local maximum or minimum, then, and also the first partial derivative exists at that point, then its partial derivative with respect to x and with respect to y must be 0. So this is a necessary condition. So which means we can easily AB is local extreme point. By extreme, I mean either minimum or maximum. Then, and f is C2, which means it is its partial derivative exists. Maybe C1 is enough. So C1 means first order derivative exists. Then you can say that its partial derivative at AB equals 0 and FYAB equals 0. So the gradient is basically 0 vector. So this is necessary condition. And it didn't tell you if you have partial derivatives equal 0 at certain point, then it has to be local extreme. And in two-dimensional case, this is often very tricky question, and it goes to some other concept which will be mentioned later. So here's the question about how to find local extreme point. So given a surface like this, we want to find local extreme values. Then we first want to apply FOC. By FOC, it doesn't guarantee you find local extreme, but it gives you a candidate of local extremes. So find all candidates of local extreme points by FOC. So which means I want to find all xy such that it satisfies FOC, first order condition, fx, fxxy equals 0 and fyxy equals 0. So here, partial derivative with respect fx with respect x is 2x minus 2x, and the other three terms are 0, so equals 0, which means x equals 0. Now for fy, this is 2y minus 4 equals 0, then that means y has to be equals 2. So the candidate for local extreme points is given by 0, 2. There's only one, so there's only one point. But we don't know if this is extreme value, either maximum or minimum, or maybe something else. So we have to do another thing, but we only need to focus on this particular point, which was derived from FOC. So we want to see how can we change that from the formula given above. So fxy, when we talk about local extreme, we often use perfect squares, which gives parabola. So for x squared, it is already perfect square, but y squared minus 4y, we can write this as y squared minus 4y plus 4, and then plus 5. That gives a perfect square. So y minus 2 squared plus 5. Then we know that this x squared, any number square is non-negative. This is also non-negative. So first two terms are greater than or equal to 0. So eventually f of xy is greater than or equals 5, no matter what xy is, because first two terms are greater than or equal to 0. And this inequality becomes equality if and only if the first two terms are both 0. So to be 0, then equal sign holds if and only if first term is 0, second term to be 0, it has to be y equals 2. So at x equals 0, y equals 2, you are going to have 5, which is minimum because it is less than or equal to any other points. So conclusion is 0, 5 is global minimum. All right, now we're going to generalize the extreme points. So an interior point of the domain of a function f of xy where both partial derivatives are 0 or they do not exist, then we call that point as a critical point. So from FOC, if this is smooth or its derivative exists, then we make fx equals 0, fy equals 0, and solve the candidate points. Those candidate points are part of critical points. And if there is something like kink, so for example, like this surface, then at this point, at this corner, there's no derivative. Then this is also critical point. And those critical points are candidates for local extremes. So we are going to look at one motivating example. So critical points are the points which it has derivative 0 derivatives, or there's no derivative. But those critical points are only candidates for local minimum or maximum. But this example tells you it could be neither one. So the function we're given is fxy equals y squared minus x squared. And this is smooth function. There's no, this, in other words, you can take derivative always. And its derivative with respect to x is negative 2x. Fy is just 2y. And make them 0 and solve for those x and y, which satisfies the FOC. So the critical points is, there's only one critical point, so you can put them as a set, but it is 0, 0. There's only one point. And now we know this is extreme point. This is not necessarily extreme point, but this is critical points, but it's a candidate of extreme points, which means it might be very high possibility it becomes either minimum or maximum. But this example tells you it could have situation, it's neither ones. So let's look at the second question. Find local extremes. Find local extremes. We have candidate. So if this is not local extreme, then there's no local extreme. Let's see. So we set y equals 0, and then fxy is fx0, which is negative x squared. So 0, 0 is minimum along x-axis. And if we set x equals 0, then fxy becomes f0y, and we change y and see along this y-axis what is the function look like. It is y squared, because this is 0, then it is y squared. And in other words, 0, 0 along this line is, oh sorry, so we have to correct this. This is maximum, and this is minimum along y-axis. So if we look at this picture from MATLAB, then along this y-axis, this is minimum, and along x-axis, this is maximum. In other words, in any neighborhood of 0, 0, it cannot be either minimum or maximum. So this is not a local extreme. So one direction is minimum, one direction is maximum. And this is called saddle point. So here, for the next question, there's no local extreme. There's no local minimum, there's no local maximum. So now we're going to define this situation we had before. So there's a critical point which is not a local maximum, local minimum, and this is likely to be saddle point. So a differential function fxy has a saddle point at a critical point AB if in open disk centered at AB, their domain points xy where fxy greater than f of AB, and domain points xy where fxy less than f of AB. The corresponding point AB FAB on the surface z equals f of xy is called saddle point of the surface. So in other words, given a critical point, if this is not a local extreme point, then we call that a saddle point. That's the definition we given here. Now our question is, given a function f of xy, how do you find the local extreme or otherwise saddle point? So there is and there is a systematic way we can explore those special points. So first, we want to list all candidate points for local maximum, local minimum, saddle point. How? By collecting all points at the boundary points. So boundary points are always suspicious for as a special point. Could be minimum, maximum, or saddle point. And another one, candidates are critical points. You want to choose critical points by setting FOC or some kink points where the derivative doesn't exist. So after you have collected those candidate points, then we have to look through which one is good for local maximum, local minimum saddle point, or sometimes inconclusive. So those points are given by second derivative test. So first derivative test is basically FOC, and second derivative test is first, if you have this quantity fx fyy minus fxy squared greater than 0, then this is local extreme point. So either maximum or minimum. So first we do this, and then if this is local extreme, you want to further explain this is maximum or minimum. So by looking at the sign of f of x. Less than 0 means in one-dimensional case, it's gonna be maximum, something like concave functions. And so this is maximum. And greater than 0, then this is convex function, which is minimum. If the sign of fx of this expression less than 0, then this is saddle point, but equal 0, then it could be anything. We don't have any information. And one remark to do this is this. So for second derivative test, we often write in terms of determinant. So we write second derivative of f, and this is matrix, and put it in the absolute value, which means determinant, which is basically fxx, fyy, and fxy, fxy. This is y. The determinant is given by, so if we recall linear algebra, if you have a, b, c, d, then the determinant is ad minus bc. So here we have fxx, fyy minus fxy squared. And the sign determines if this is greater than 0, then this is local extreme. If this is less than 0, then this is saddle point. And if this is equal 0, then nothing, we cannot conclude anything. Nothing can be concluded. And if this is local, so if greater than 0, if this is local extreme, you won't tell me is it minimum or maximum by looking at the sign of fxx. All right, here we are going to look at the last example. So we have f of xy, which is a mountain surface given by this formula, but the region bounded by the lines 0, 0, y equals 0, and y equals 9 minus x. So our domain is x equals 0 means y-axis, and so let me put it this way. So, and y equals 0 means this one, and y equals 9 minus x, so it is 9, and slope negative 1. Yeah, so approximately like this, and we're looking at the area inside of here. And we have a tent or a surface on top of this triangle area, and so what want to see the the question is, what is absolute max or minimum? So the candidate points we're going to find is so first we have boundary points, candidates. So boundaries are, so there's three sides as boundary of triangle. So let's say first part of the boundary is, I would say, this area, which is, I would write this R1, which is x, y, where x is running from 0 to 9, but y equals 0. The other one is line 2, which is xy. We have x equals 0, but y is running from 0 to 9. So this is R1, this is R2. R3 is all xy's such that x plus y equals 9, and let's say x is between 0 and 9. So those are from boundaries. And number 4, critical points. So the critical points is from FOC. We need to solve FOC. So fx equals 2 minus 2x equals 0, and which gives me x equals 1, and fy equals 4 minus 2y equals 0. And then if you solve, then we have y equals 2. So together we have critical points 1, 2. This is the only critical point. So 1, 2 is approximate. It's very like here. So somewhere here. So to find out absolute maximum, absolute means global maximum or minimum in this triangle area, what we search is not all yellow parts. We only focus on this particular point and those lines giving the boundary. So we are going to so we're going to first look at what is the function value along at the point here. All right, I'm going to copy this to the other page. So first I'm going to calculate the function value where critical point is located. So f of 1, 2 is going to be 2 plus 2 plus 8 minus 1 minus 4, which is 7. I want to see if this is global maximum or minimum. And also along this line, So in other words, along this line, what the function values are, or you can think of the height of the mountain surface along this line, then, so this is for 4, and that for 1, I have along L1, fxy is, because y equals 0, so those things are 0. X is just 2 plus 2x minus x squared. And and x is in between 0 and 9, we can look at its perfect square case. So when I put this 3 minus 1 plus 2x minus x squared, then this is, from here I can write this as x minus 1 squared. And we know that this guy is non-negative, so this guy, so 3 minus some non-negative number is less than 3, so it is greater than 3, and equal sign happens when x equals 1. So at x equals 1 and y equals 0, at this point you have a local maximum. But yeah, I think and we can think of, yeah, so we are going to look at, so f10, which gives me 3, right? This is, so let me mark this. 7 is one thing and 3 is one thing. Also, I want to look at those corners. So those corners are given, maybe we can, yes, and those corners are f00, another one. So f00 is from here, everything here with variables will be 0. So 2 is the value. And another corner here is 90, f90, which is 2 plus 18 minus 81, which likely to be minimum, so negative 61. Number 2. So number 2, L2, we're looking at this line, and this line means x equals 0, y is ranging from 0 to 9. So fxy, so 2 plus 2 times 0 plus 4y, and minus 0 squared minus y squared, and again we do 6 minus 4 plus 4y minus y squared, and we have 6 minus y minus 2 squared, and y is changing from 0 to 9, right? So in that case we get, so we have at y equals 2, this takes maximum, so fy equals 2, but x equals 0, then this is 6. This is one thing, but if you have the corners for this L2, the corner, we have calculated one corner already, so the other corner here is going to be, so f09, right? f09, which is 2 plus 36 minus 81. So that gives me 43, negative 43. And number 3. For number 3, we only need to look at the interior of L3. We don't need those corners because those corners are already calculated here and here. So for L3, this is for x plus y equals 9, and x is ranging from 0 to 9. And for here, we can do this by substituting y by 9 minus x, so that for 3, which is L3, so fxy is going to be 2 plus 2x plus 4 times 9 minus x squared minus 9 minus x squared. And we do simplification. Plus 18x minus x squared. So we have second order term negative 2x squared. First order term is 20 minus 4, which is 16x. And constant term is 38 minus 81. And we can take out negative 2 here. Then x squared minus 8x minus 43 and negative 2. And this can be completed by, I need to 16 here. Then because we put 16, we have to cancel this out. So this is by multiplying negative 2, that means negative 32, so plus 32. So this is plus 32 minus 43, negative 2, x minus 4 squared minus 11. So at this, the extreme point, and along this line is at when x equals 4, then y is, because we set 9 minus x, y equals 9 minus x. So when x equals 4, y is 5, and this is negative 11. And it's going to be less than negative 11. All right, now we had a couple of candidates. So we want to choose the least number as the absolute minimum and the greatest number as absolute maximum. So now we have 7, 3. So the highest point is 7 is highest over all those numbers. So we can mark this as maximum, absolute maximum. And for the minimum, we have 3, 2, negative 6, 1 likely to be the smallest one, because negative 43 and negative 11, right? So we have absolute minimum here. This is absolute minimum. All right, this is a little bit complicated problem because we have to take care of those boundaries, which is not very convenient. But the calculation itself is not. It's lengthy but not hard. All right, we're going to stop here.